Hello, students. Today we're going to be talking about something called identities, which are a little bit weird. It's kind of like a puzzle where you have to figure out why two things are the same, and you have to do some really specific steps to show that. A lot of times we call these things trigonometric proofs, and they certainly are that. They are a logic-based thing. But if we think about them as puzzles, I think that makes it a lot easier for us to digest. The big idea for an identity is that we have different ways of writing things that mean the same thing. We've talked about this with reciprocal functions, that secant and cosine are reciprocals. We could also say the same thing in terms of cosine of x is 1 over secant of x, and sine of x is 1 over cosecant of x. And the same thing would be true for tangent of x being 1 over cotangent of x. What this means is that these things are identical, cosine and 1 over secant, or secant and 1 over cosine, but they look different, which is kind of an odd thing. So we have some reciprocal identities. We have two quotient identities as well. We have one of them listed here, which is that cotangent of x is going to be cosine of x over sine of x. The other quotient identity is going to be tangent of x, which is going to be sine x over cosine of x. And I'd like you to just recall that if we have an angle in a unit circle, we've got the coordinates x comma y, that in this situation, we said that cosine of theta is equal to x, sine of theta is equal to y, and we said that tangent of theta, which is the opposite divided by the adjacent, would be y over x. Based on that, that makes a lot of sense why if sine is y, cosine of x, and tangent is y over x, that tangent is sine over cosine. This is where these identities come from, these relationships that we can build with some trigonometry. And we're going to use them to try to decide whether or not some statements are true. As an example of this, we've got a statement sine of x times secant of x is equal to tangent of x, and we have to decide if this is true or not. There are a couple of rules that we have to follow for this. And the biggest rule is we can only touch one side. This is what makes this different from solving an equation. Our goal is going to be to show that these two things are equal, and to do that we can only affect one side, trying to change it step by step to show that these statements are the same. The second thing is our goal. Our goal is to have our last line of this be something like tangent of x is equal to tangent of x. To show that even though these things look different, they are possibly the same exact thing. And then I'm going to talk about our major strategy here. Strategy. There we go. I can spell. So we're going to have two pieces to this. The first is to work on the most complicated side. It's easier for us to go from more complicated to less complicated. Oftentimes, we'll see this on the left side. And the second is we have lots of ways to convert to sine and cosine. So if we can do that, we can come up with some effective ways to get this into another form. So looking at this, I've got sine of x, and I can't really do anything with that. Secant of x, I happen to know that secant of x is equal to 1 over cosine of x. That's one of our reciprocal identities that we talked about on the previous page. If I substitute that in, so we're going to make our second line sine of x, and instead of secant of x, I'm going to write this as 1 over cosine of x. Now I know I can multiply these things on the left. I've got sine of x over 1 times 1 over cosine of x. That lets us multiply that as sine of x over cosine of x. This right side stays the same. And I'm going to use my second relationship here, which is that I know that sine x over cosine of x is a thing. That's equal to tangent of x. Because of that, I'm going to substitute that in. And we've got tangent of x is equal to tangent of x. The fact that we got both of these to be the same exact thing is the goal here. So this would be considered a successful identity. Let's look at another one of these. In this case, we're trying to show that these two sides are equivalent. I identify that the left is the more complicated side, and I'm going to go kind of piece by piece here and to try to convert everything into sine and cosine. So let's do that. So we've got cotangent of x, and I have an identity for that. So cotangent of x, we said was equal to cosine x over sine x. You should have maybe a page somewhere that has these written down, or maybe just press back a couple times in your Jamboard. So I'm going to rewrite that as cosine of x over sine of x. All right, sine of x is already sine of x. I'm going to keep that the same. And then we've got secant of x. And I know that secant of x is equal to 1 over cosine of x. So I'm going to write that here, 1 over cosine of x. And the equals 1 stays the same. Okay, let's combine some fractions by multiplying. So cosine times sine, I'm going to write that as cosine x, sine of x. And then the bottom, we've got sine x times cosine of x. Sine x times cosine of x is equal to 1. And then algebraically, we can see that we've got the same thing on the top and the bottom. So that means that 1 is equal to 1. This identity is complete. Looking at the same thing on this one, I'm going to add one note here because we haven't talked about this yet. We have a weird thing with trig, and there's a reason for this. If we have some kind of trig expression, so tangent squared of x is what I'm talking about here, that means the same thing as tangent of x squared. The reason that we put the squared with the tangent is so that we don't think that that is tangent of x squared, which would be a different thing. If we were consistent about using parentheses with things, we wouldn't have had to do this, but we as humans are pretty terrible at that. So we have to be really careful with what's going on there. Okay, so I'm going to do the same thing. I'm going to take a look at my left side. That looks like the more complicated side. And I'm going to start to identify pieces. So secant of x is 1 over cosine of x. So we've got sine x times 1 over cosine of x. We've got the big divide. And then I've got cotangent of x, which is cosine x over sine x. All right, so I'm going to put that on the bottom. Don't love that this is a fraction over a fraction. So I'm going to do two things at once here. The first is multiply the top, sine times 1, 1 times cosine. We get sine x over cosine of x. The second thing is I'm going to write this as a side-by-side division problem. And when I do that, that makes it a little bit easier for me to process that we've got sine x over cosine x. I'm going to change to multiply and flip, give me sine x over cosine x. One of the things that you might notice is that here we have sine x over cosine x, and we know that that's equal to tangent of x. So what's really going on here is we've got tangent of x times tangent of x. If I'm multiplying those by themselves, that's equal to tangent squared of x. And just to be consistent, I want to make sure I copy this stuff on the right side all the way down so that I'm not being sloppy with my work. And when I do that, we get tan squared x equals tan squared x. Okay, looking at my next one, it looks like the left is the complicated side again because I have two pieces there. Secant is 1 over cosine of 2x. Even though it's a 2x, I'm just going to keep the inside the same. So I could rewrite this as sine of 2x, tan of 2x on the other side. And then I'm going to switch out secant of 2x for 1 over cosine of 2x. That gives me sine of 2x over cosine of 2x, I forgot my 2 in there, is equal to tangent of 2x. And we know that sine of 2x over cosine of 2x is equal to tangent of 2x. That says 2x, although it looks like scribble. So we get tangent of 2x is equal to tangent of 2x. The other set of identities that we're going to talk about are Pythagorean identities. These come from the relationship that we know in a right triangle, where we can say that x squared plus y squared is equal to our hypotenuse squared. And we have a weird thing that goes on in our unit circle, because in all of these cases, the hypotenuse is equal to 1. So because of this, we can say x squared plus y squared is equal to 1 squared, which is just 1. If I think about this in terms of x and y and cosine and sine, this becomes cosine squared of x plus sine squared of x, really should be theta, but I'm just making that x here, is equal to 1. That's our first Pythagorean identity, which is a really cool thing. So cosine squared x plus sine squared x is equal to 1. We often use this in 2 other different forms, based on getting either cosine squared or sine squared by itself. Those are really, really useful in terms of what we're looking at. So we can say that cosine squared of x is equal to 1 minus sine squared x. And going the other way, we can say that sine squared x is equal to 1 minus cosine squared x. The other thing that we can do with these is to develop some other Pythagorean identities from the original ones. So if I start with the statement cosine squared x plus sine squared x is equal to 1, if I were to divide this whole thing by like cosine squared x, and I'm going to divide each piece by that, what this does is give us a new way to think about this. So cosine squared over cosine squared is 1. Sine over cosine, well, that's tangent. That's kind of cool. And 1 over cosine squared, that's going to be the same thing as secant squared of x. So our next Pythagorean identity, if we've got our primary one here, our second one is going to be 1 plus tangent squared of x is equal to secant squared of x. We could also flip that around by minusing 1 to both sides, but I'm not going to show that here because I figured that's an okay thing to not show. The other thing that we can do is if we have cosine squared x plus sine squared x is equal to 1, well, what if this time I divide everything by sine squared of x? The same thing's going to happen, so we've got cosine over sine, that's cotangent. Then we've got sine over sine, that's going to be 1. And 1 over sine is cosecant squared of x. So our third Pythagorean identity, and again, all of these just come from the first one, which is sine squared plus cosine squared is equal to 1. And that gets us cotangent squared x plus 1 is equal to cosecant squared of x. These are our Pythagorean identities. I recommend that you have them written down somewhere so that you can make use of those moving forward. All right, let's try a couple of these identity things to see what's going on here. And in the first one, I'm going to make use of identifying the reciprocal thing here. And 1 over secant is going to be cosine. So let me write that just down the side. That means that if I substitute that in, we're going to have sine squared x plus cosine squared x is equal to 1. Now I'm going to use that Pythagorean identity. This is going to feel a little bit weird as a step because all we're doing is saying that this equals 1, and we have our final identity step saying 1 equals 1. For the one down below, I've got to do a little bit of work first. I've got to identify that these two pieces have something in common. They both have a cosine of x. So I'm going to factor a cosine of x out of both of these. And if I undistribute a cosine of x, I'm going to have a 1 minus cosine squared of x, because 1 times cosine is cosine. Cosine times cosine squared would be cosine to the third. Okay, I also know that if sine squared x plus cosine squared x is equal to 1, if I move cosine to the other side, sine squared x is equal to 1 minus cosine squared x. So that part in the middle is going to be switched into sine squared x. On the outside, we've still got that cosine of x. And we've actually gotten to our answer here, cosine of x times sine squared of x. We're done at that point. Let's take a look at another couple of these. Again, the one on the left, in fact, in both of these, looks more complicated than the one on the right. So let's see what we can do here. This one looks kind of like the one we just did, where we have something we can factor out. So I can take a sine x out, leaving me with sine squared x minus 1. The stuff on the inside, that's not quite what I had before. So one of the ways that I might deal with this is, again, to use my Pythagorean theorem identity. So we've got cosine squared plus sine squared x is equal to 1. Maybe I'll substitute this in for the 1. And when I do that, we've got sine of x out front, sine squared of x, and if I'm putting this in for minus 1, that's going to be minus cosine squared x minus sine squared x instead of 1. That gives me sine squared minus sine squared. We have sine x times negative cosine squared of x, which is the same thing as this if I move that negative out front. So negative sine x cosine squared x is equal to negative sine x cosine squared x. For the next one, I'm looking at these and I'm going to do the same exact thing. I see that these both have a sine squared in front. And if I were to factor out a sine squared of x, I've got 1, and then I've got plus cosine squared x. And interestingly, that's exactly what I have on the other side. So once I've factored, I'm done with this problem. All right, so looking at this one, and this is the last of these ones that we're going to look at, I'm going to pay attention to what I had for my Pythagorean identities for like tangent and cotangent. And if you remember, both of those came from this idea that if we have sine squared plus cosine squared x is equal to 1, when we divide this whole thing by cosine squared, we end up getting tangent squared x plus 1 is equal to secant squared x. So what I'm going to try to do is to convert this into the other form of these things. So on the bottom, I've got 1 plus tangent squared x. I'm going to rewrite that as secant squared of x. And on top, if I take 1 away from both sides, I see that I've got secant squared of x minus 1, which is tangent squared of x. Cool. Not all the way there yet. I do know that I can convert these things into sine and cosine now. So sine over cosine is equal to tangent of x. So I'm going to write that as sine squared x over cosine squared x. And then I'm going to divide and just do this horizontally, because secant of x is equal to 1 over cosine of x. So I'm going to write that as 1 over cosine squared of x for secant of x squared. All right, I know that dividing is really multiplying by the reciprocal. So we've got sine squared x over cosine squared x times cosine squared x over 1. Those cancel out, leaving me with sine squared x is equal to sine squared x. That's my final step there.